This presentation by Cordell, Trevor, Danny, and Ryan is on concrete admixtures.
Air entrainment can increase the freeze-thaw durability of concrete. This admixture can be used to create a more workable concrete compared to the non-entrained concrete, while also reducing bleeding and segregation in the fresh concrete. Entrained air bubbles that are formed within concrete act as a physical buffer aiding against cracking caused by stresses due to water volume augmentation in freezing temperatures. Water-reducing admixtures are chemical products that when added to concrete can create a desired slump at a lower water-cement ratio than what is normally required. Water-reducing admixtures are often used to obtain a specific concrete strength using lower cement content. Lower cement contents result in lower CO2 emissions and energy usage per volume of concrete produced. Through this type of admixture, concrete properties are improved and they will help with the placement of concrete under harsh conditions. Superplasticizers result in substantial enhancement in workability at a given water-cement ratio. They are also used as a major application in the production of high-strength concrete. Superplasticizers are often used in producing a concrete that can flow in a heavy reinforced structure or inaccessible areas. Shrinkage reducing is an admixture that is added to the concrete during the initial mixing that could reduce early and long-term drying shrinkage. They are typically used in situations where durability problems could occur due to shrinkage cracking or where large numbers of shrinkage joints are undesirable for economic or aesthetic purposes.
Retarders work by stopping or slowing the reaction rate of tricalcium silicate and the growth of calcium hydroxide crystals. These two components are what causes the cement paste to harden, and by slowing or temporarily stopping this reaction, the concrete will remain workable. Only once the retarder additives have fully reacted with the cement mixture can the hardening process begin. Set time retarders are used in several scenarios. When pouring at high temperatures, retarders must be used so that the cement paste does not harden en route to site or before finishing work is done. Retarders are also used in large pours and in pavement to avoid cold joints. Cold joints are when part of the cement hardens before you finish all the pours. Accelerators work in two different ways. The first way an accelerator can work is by acting as a catalyst for the hydration chemical reaction, increasing the rate at which hydration occurs. The other way an accelerator can work is by weakening the crystal formation, which allows water to flow through the cement paste uninhibited and react with more of the paste at a faster rate. Accelerators are commonly used in cold temperatures so that the cement paste can develop strength before it freezes. Accelerators are also used in any pours that require early strength, such as tunnel construction. A common concrete admixture is fly ash. Fly ash is the byproduct of coal burning and consists mainly of silica, aluminum oxide, iron oxide, and calcium oxide. Fly ash particles are very small, averaging about 150 nanometers in diameter. The addition of fly ash has several different effects on concrete. Concrete with fly ash absorbs more water due to the fine particle size and high surface area per unit volume. The concrete strength also increases with more fly ash up to an optimum value. Fly ash can decrease the permeability of concrete and therefore increase the chemical resistance and durability. Since fly ash can partially replace Portland cement, this admixture can reduce the carbon footprint of the concrete and be more environmentally friendly.
Silica fume, also known as microsilica, is a byproduct in silicon metal or ferrosilicon alloy production. This admixture has been used to enhance material properties and partially replace Portland cement for over 30 years. Silica fume consists of very fine particles, nearly all of which are finer than 1 micrometer. Silica fume has some significant impacts when added to concrete. Silica fume will reduce the slump and make the concrete more cohesive. It will additionally raise the strength of concrete with respect to the compressive strength, bond strength, and abrasion resistance. One thing to keep in mind with silica fume concrete is that the surface dries relatively quickly. As a result, it is important to moist cure the concrete in the early stages. Overall, silica fume provides a number of benefits when used as a concrete admixture. When using an admixture to improve the fire resistance of concrete, the goal is to increase the strength and maximum exposure time when it is exposed to elevated temperatures. This can be accomplished by the use of mineral and chemical admixtures. These fireproofing admixtures are admixtures that are regularly added to concrete for different purposes, but have a positive effect on the concrete when exposed to elevated temperatures. Some of the mineral admixtures that can positively affect concrete at elevated temperatures include polypropylene or polymer fibers, ground granulated blast furnace slag, or just slag, fly ash, and carbide waste. We looked at two main studies for the mineral admixtures. The first compared slag and fly ash. The second looked at carbide waste. In the first study, concrete with mixes of slag and fly ash were analyzed at 600 degrees Celsius. It was found that when some of the cement is replaced with slag or fly ash, the strength of the concrete will only deteriorate at about a quarter of the normal rate. So the use of slag and fly ash not only reduced the weight of concrete, but they significantly improved the performance of concrete during a fire. The second study analyzed carbide waste based on how much cement was replaced with the carbide. It was found that by using the proper amount of carbide, the compressive strength of concrete will actually increase as the temperature increases until 600 degrees Celsius. The downside, however, is that the strength of the concrete at normal temperatures will be lower. Some of the chemical admixtures that can positively affect concrete at elevated temperatures include accelerators and retarders. We looked at one study that compared the effects of accelerators, retarders, and superplasticizers at elevated temperatures. However, the superplasticizer was found to have no effect on fire resistance. The chemical admixtures tended to increase the amount of time and temperature that the concrete can be subjected to before failing. By adding an accelerator to the concrete mix, the concrete could safely withstand up to 600 degrees Celsius, as opposed to the normal 500 degrees, and a retarder added about 50 degrees to bring it to a max of 550 degrees Celsius. That concludes our presentation on concrete admixtures. We'd now like to open the floor to any questions.